All right, so we've got the chart up here, and I will go back and talk about 3 through, what number was that? 3 through 12. We'll talk about those here in a second as well, but I want to start with number 25. You've got this function here, f of x equals square root of x. Is it plus or minus? Minus 3 over x, all right? And we're supposed to do this whole, find the global max and min, all right? So what did we say yesterday? Where are the only places that absolute max and mins can occur? Endpoints or stationary points. Now when I say the only place they can occur, we got to be really clear because this is going to come about in number 44 as well. The only place the max and min values of this function can occur are at the endpoints, and we were given the endpoints of 0.25 and 1, or at the stationary points where the derivative of the function is 0. So what we're going to need to do is the derivative of this function. Well, before we do the derivative, we want to write this as a power, so we can use our power rule. Okay. All right, so the derivative of this is how much? What would I get? 1/2 x to the negative 1/2 3x to the negative second. Okay, so we got to be able to do that power rule. Obviously, that's going to be very important for what we want to get done here for this next quiz coming up. Then we want to set that equal to 0. All right, now this is no calculator. All right, we need to be able to do this no calculator. One of the reasons we're going to review tomorrow these various types of functions and how to solve them and so forth. So there's nothing very obvious to do there. You know, in the other problems, it was just some simple factor out an x, factor out a 2x. You know, they were pretty easy to solve algebraically. This one, not so much. So when we start getting these radical or fractional exponents, and we get these negative exponents, and you're working on it no calculator, your best bet at this point is to rewrite them with positive powers, and maybe even write them as radicals. So this one, negative power, that would go down to the bottom with the 2. The 1/2 means square root. So this would be equivalent to that. So it'd be best to write it that way. Plus, and then this x would go to the bottom, not the 3, just the x. Okay? So this is what I'm actually solving right here. All right, there's my f prime. Now, you know, what do I do to try to solve that? Well, to be honest, at this point, when you get into a function that's a little bit out of the ordinary, you should stop and kind of think about domain issues, and you should think about those kind of things. I've got something plus something equaling 0. Well, the only way that can equal 0 if one of them's positive, one of them's negative, right? The only way you can add two things that make 0 is one's positive, one's negative, or they're both 0. Will this fraction ever be 0? How does a fraction ever equal 0? The top is 0. Well, that'll never happen here, and it'll never happen here. So these two are not going to be 0. So the only thing they have is one's positive, one's negative. Then I start looking at my domain. Matter of fact, let's go back to the original function. We talked earlier in chapter 1 about natural domain. Can x ever be negative in this function? You can't have a negative square root. X can't ever be 0 in this function, right? So we know they didn't write it, but we just know by looking at the function that x has to be positive all the time in this particular function. So when we come down here, and it can't be 0, right? Well, what's that tell you about this fraction? What's that tell you about this fraction right here? It's always going to be positive. No matter what I put in for x, it's always going to be positive. What about this one? Same thing, because it's squared, right? But then again, since x is positive, it doesn't even matter it's squared. These are both going to be positive, and if you add two positives together, it's positive. So this will never equal 0. So we need to be able to analyze functions that way. Now, we'll get better at it as the year goes on. I don't expect you to be experts at it now, but you certainly need to be able to think about those things. All right, so I would write here, there are no stationary points on this one. Now remember, what we were looking for are the possible places where max and mins can be. And they happen at the endpoints and at the stationary points. Well, this function has no stationary points.
So could it possibly be?
It could be the e to the x graph. Think about e to the x. It never has a place where the slope is 0 either, right? It doesn't, it could be a line. Well, it's not a line. I mean, if it was a line, it would look like mx plus b, right? So it's clearly not a line. But it is something that just has no flat spots. It has no places where the slope is 0, okay? So when we go to do the list of candidates, now, in a problem like this, we have a couple of choices. Now, I taught you this list of candidates thing yesterday because that, quite honestly, since we have to justify a reasoning why something is a max and a min, the list of candidates is just one that seems to work in almost all cases. There's a few cases where it doesn't work. We'll talk about those later. The list of candidates is a pretty good one to use. So I'll go ahead and do that. Well, our only two candidates then are endpoints. So we need to take and put our two endpoints into our function. And we come back up to here. Now remember, 0.25 is 1/4, so it'd probably be easiest to put in 1/4, because what's the square root of 1/4? 1/2, right? So that would be 1/2, assuming this is no calculator. 3 divided by 1/4 is 12. So 1/2 minus 12 would be negative 11.5. Okay? And then put a 1 in. Square root of 1 is 1. 3 over 1 is 3. That's negative 2. So here is my max right here, and here is my min right here. Those are my only two candidates. So I know it has to be that. So then you'd be done. Okay, and that's what should all be on your paper. You should have all that. Now, and your justification is your list of candidates. And your work here showing, hey, there are no stationary points. So what you've shown by that work is I know that where all the possible max and mins can be, endpoints and stationary points. I've shown there aren't any stationary points. Here we go. Now, we could have done this without a list of candidates. Come back to what I said right here. What did we say about this in the box? Always positive. What do we know if f prime is always positive? F prime is always positive means f is increasing. So I could have stopped right here and said, hey, f prime is always positive. So f, therefore, is always increasing. If f is always increasing, where's its minimum? At the left endpoint. Where's its maximum? At the right endpoint. Now, to answer the question, we still needed these values, right? The question was, what are the max and min values? So we still needed to calculate the values. But I could have used as my rationale, instead of a list of candidates, I could have said, well, since f prime is always positive, f is always increasing, minimum's at the left end, max is at the right end. Okay, so that brought up something just a little different than you saw in number 23. Okay, let's go to number 44 and take a look at that one. It says, for what values of x does the slope of the tangent to the curve take on its largest value? Okay, so Josie, what's that equation there in 44?
Y equals negative x cubed plus 3x squared plus 1.
Plus what?
1.
Plus 1. Okay, somebody go ahead and graph that on your calculator real quick. Just graph it, and we'll come back and look at that graph later on. But all right, so where does the slope of the line tangent to this curve take on its largest value? Okay, so just thinking about it graphically for a second. All right, got a presenter here. All right, the slope, where does the slope of this take on its largest value? So let's first understand what they're asking for. Well, what are the slopes over here? Negative. So that's not very big, right? And now they're getting what? Less negative. Now, does that mean they're getting bigger? Less negative means it's getting bigger as a value, right? Okay, so the slopes are getting bigger, and then the slopes are positive, right? And getting more positive, right? So the slopes are still getting bigger, right? Still getting bigger, and then somewhere in here is the inflection point, right? And then what happens to the slopes? Positive getting less positive, so they're actually getting smaller, right? The value, the slopes are getting smaller. And then they're negative and getting more negative, so again, still getting smaller, right? So where would you expect this to happen? Inflection point, right? Okay. That's just something to kind of keep in mind here for a second. Just so we understand the question, all right, of kind of what's happening. Now, let's forget we ever looked at that graph, and let's just take the words of the problem. It says, where do the slopes of this take on their largest value? Sounds like a max problem to me, right? We want to find the maximum. We will find the maximum of what? Yesterday we did a volume of a box, and we wanted to find the max volume. So what we did is we took the volume equation, and then we looked at its derivative, because where do maxes occur? The maxes occur at the endpoints or at the stationary points, which is the derivative of the thing we're trying to maximize. We're trying to find maximum slope. So we need, so David, go ahead, say it again.
We have to find the derivative of the derivative.
That's right. Because what we're looking for, if we're finding the maximum slope, we need to write a slope equation. And what do we call the slope equation? The derivative, right? Y prime. So let's find Y prime. And that will be negative 3x squared plus 6x. The derivative of 1 is, okay? Aren't we trying to find the maximum of this? Now, several people that I helped were making the mistake of finding the maximum of this, right? You're thinking you're finding the maximum of this function. No, what we're finding is the maximum of that function. We're finding the maximum slope. Well, the way you find the maximum of any function is you look at the endpoints, which they didn't give us any, and you look at its stationary points. What are the stationary points of this? David, say it again.
Where the derivative is 0.
Where the derivative of it is 0. So we're looking for the stationary points of Y prime. So we need to find when Y double prime is 0. Right? So that'd be negative 6x plus 6 equals 0. Negative 6x equals negative 6. X equals 1. That's one of our candidates where the max should occur. Now, they didn't give us any endpoints. Sometimes that happens. Sometimes, okay, and think about it. Think about what Y prime is. What kind of graph is Y prime if you were going to graph it? Parabola, upside down. So, we don't really need endpoints because we know where the max is going to be, right? It's going to be at the stationary point, right? So, but this brings up a problem. You can't have a list of candidates when you only have one candidate. Because what's the whole point of having a list of candidates? What's the point of having a list of candidates to find a max and a min?
You find what comes the highest and lowest.
To compare, right? You got to compare. You look at your list of candidates, you say, hey, this one's the highest, this one's the lowest, because you're comparing. Well, if you only have one candidate, how do you know if it's a max, how do you know it's a min? You got to go beyond that. So you can't do a list of candidates when there's only one candidate. So what you have to do is some other rationale. You got two choices. You can do a number line, like we learned yesterday. Or in this one, since it's so easy, we could just say, well, Y prime's a parabola facing down. It's only going to have one stationary point. It will be the max, right? And you can just write that sentence and justify it. You have to justify that it's a max, though. Now, if you don't think about that with the parabola, then just go to a number line. This is something you guys will come to learn as we go through the year. You want to do a list of candidates. You only have one candidate. Do a number line, since it's the only candidate. So I'll put a 1 on that number line. I'm going to label it Y double prime this time, right? Because that's where our candidate came from, was Y double prime. Pick a number over here. Pick a number over here. I'm going to plug it back into Y double prime. Put a 0 in there. I get a 6, which is positive. Put a 2 in. I get negative 12 plus 6. That's negative. So clearly I have a max, because it goes from positive to negative. Y double prime goes from positive to negative. Now again, I'm talking about max of Y prime. Let's come back to the chart here. All right. I'm down here. I've got y double prime is changing from positive to negative, so therefore y has changed from increasing to decreasing. That's a max. And this was the slope equation, so the max is there. Now what does it say? Let's answer the question.
At what?
At what x value? So, it happens at x equals 1. Now, this is a really neat problem though. Let's go back to our graph. Uh-oh. Okay. Okay, let's go back to our graph. And sure enough, at 1 is the inflection point. So what we just did in disguise there was found the inflection point, didn't we? We found the inflection point. Now let's back up a minute, okay, and let's pretend this problem had said something else. Let's pretend this problem had said, find the inflection point of this function here, okay? Well, how do you find the inflection point? Well, what's an inflection point? A place where the concavity changes. How do you show the concavity changes? You show that you switch columns. What's the easiest way to show? Is it easy to show that a function's increasing and decreasing? No, actually, it's much easier to show that a function switches from positive to negative. That's what the number line does for us. So if this question would have been find the inflection point of this, we would have done exactly that same work. We would have said, hey, to find the inflection point, I need to see when the second derivative changes from positive to negative. Where does that happen? Usually it happens when the second derivative is 0. So I just said, let's do the second derivative. Let's set it equal to 0. Now, the only thing would have been different instead of writing stationary point here, because we were talking about y prime, so it was a stationary point of y double prime was a stationary point of y prime. I would have wrote possible inflection point here, right? I just said, okay, where the second derivative is 0 is a possible inflection point on the original function y. How do I show that it actually is an inflection point? I have to show it changes concavity. I do that by showing it switch columns. Right here, y double prime switch positive negative tells me y switch concavity. All the same work would have been there. It's kind of interesting to think though that inflection point is where you have the steepest slope, right? We treated it as a maximum problem, the max of y prime, and it all worked out the same. All right, one more thing here. Let's look at number 54. Number 54 says this particle x, we had number 54, right? Okay, 3t to the 5th minus 25t cubed plus 60t. All right, and we are supposed to find when the particle's moving to the left. Okay? So what did we say about that yesterday? What's happening when a particle's moving to the left? Negative, what? Derivative. Negative velocity, right? Always remember position, velocity, and acceleration have that derivative relationship. When the velocity is negative, the particle's moving to the left. Because what's happening is position is decreasing. If the particle's over here on the x-axis at 10, and then it goes to 9, then to 8, then to 7, it's moving to the left. Its position is decreasing. If I'm at 0 and then go -1, -2, -3, the position is decreasing. When the position is decreasing, according to the chart, the velocity, its derivative, is negative. So what I care about is when x prime is negative. That's what I'm finding. Well, the way to find that is find when it's 0. Okay? Because tell when it's stopped. Then you can tell when it's going to the right and the left. So we get 15t to the 4th minus 75t squared plus 60. And we want to set that equal to 0. Okay? What do we do algebraically for that? I would take out a 15. Okay? That would make it much easier. Then you get t to the 4th minus 5t squared plus 4. Now we can FOIL this. We'd have t squared and t squared. We have 4 and 1. Okay? Then what? You could factor them again, plus or minus 2, plus or minus 1, right? And so your answers are going to be, and the 15 we can ignore because that'll never equal 0, right? 15 will never equal 0. So t is either going to be
plus or minus 2,
plus or minus 1, and if we look at 54, it says t is greater than 0, so we can ignore the negatives. So we can just worry about 2 and 1, and those are my stationary points. Okay? So at time 2 and at time 1. Now sometimes you want negative for time. You know, if noon is time 0, then negative 1 would be at 11 a.m., right? So sometimes you use the negatives, but in this case they told us not. So when does it move left? So what's my next step? Number line. And I label that x prime because I want to know when x prime is negative. That's what I'm looking for. That's when the particle's moving to the left. So I put a 1 on my number line, I put a 2 on my number line, and I'm going to pick some points in between. And the factored version of this is usually the place you want to plug stuff into. Okay, the factored version is the where you want. So you put a 0 in here, that'd be negative. 0 there is negative. Negative times negative is positive. 1.5 squared. Even if you don't know what it is, it's certainly got to be less than 4, doesn't it? Because 2 squared is 4. 1.5 is 2.25. Minus 4, so that's negative. 1.5 squared is definitely bigger than 1, so this will be positive. Positive times negative is negative. And then a 3, 9 minus 4, 9 minus 1, those are both positive. It doesn't always alternate. You don't want to assume that it'll always just alternate. Somebody asked me yesterday, it was a really good question. They said, how do you know, like on this one, if we want to know when it was going to the right, we would say, well, from 2 to infinity. And the question was, well, how do you know to infinity? How do you know it doesn't change back to the left again later? How do we know? Because these are the only stationary points, which means these are the only times it stops. These are the only times the particle stops. Okay? So there's no way it can go back to the left without stopping. And so since we found the only stationary points, we know this now goes to infinity both ways. All right, the question was, when's a particle moving to the left? Well, that would be between 1 and 2 seconds, because that's when its velocity is negative. That's when the position is decreasing, is when its derivative is negative. So again, all this stuff is stuff we got from the chart. Okay, but this all has to be there. Okay, just an answer isn't good enough. You got to have your derivative. You got to set it equals 0. Find your station points. You got to have this number line. All right. Okay. Well, we are going to get to practice some more of this local max min stuff with trig functions, with exponential functions. You know, these should be the easiest of the bunch because the algebra is the easiest probably of these compared to the other stuff. But that's why we're going to spend more time working on those as we go along. All right. 46. Let me give you a hint on 46. It says show that f has either no local extrema or a local max and local min. Now in 46, what kind of function do you have there? Okay, cubic. And so what they are essentially saying is that if you're going to have a cube, a cubic function could do this. It could actually have a flat spot and do that, or it can go up and do this. So essentially, there's no max or min here. There's no max or min here. Here there's both a max and a min. So essentially what they're saying is, could we prove algebraically that anytime you have a cubic, you're either going to have all or nothing. You're going to have both a max and a min, or you're going to have no max or min. All right? Well, it comes down to this. If you do the derivative, I'll help you with this, this first part of it. If you do the derivative of that thing, what do we get? Y prime would be, or f prime, I guess, would be what?
3ax squared plus 2bx plus c.
Okay? It's a parabola, right? Now, to find the local max or min, we've got to set that equal to 0, correct? Right? That's where we look for our max and our min, is at the stationary points, right? And it's a parabola. Now, what are the possibilities for a parabola equaling 0? What are the,
one if its vertex hits the x-axis or if both be.
right? So those are the three possibilities for a parabola that opens up, and if A happens to be negative, it open down, but it'd be the same scenario, right? So this is my y prime, or my f prime, okay? So it might not hit 0 at all. If it never equals 0, then there are no stationary points of y, and so therefore it would be more like this first one, right? The slope is never 0. Or we could have this, which means what? Flat spot, right? It's y prime is positive and then stays positive. So slopes are positive, then are 0, then stay positive. Again, no max or min, right? And then the other possibility is it crosses twice. And what has to happen? Both a local max and a local min. So that would be a good justification right there for part A. Okay? And that kind of goes with that first one we did today, number 25, where we just think our way through on y prime. Instead of trying to solve this mess of a thing with a's and b's and c's, we just think about what it is and what are all of its possibilities. Okay, the second part in B uses a quadratic theorem, a quadratic formula. If we were going to solve this as a quadratic, right, and you may remember the quadratic formula. The quadratic formula said that if you have ax squared plus bx plus c equals 0, its solutions are when x is negative b plus or minus the square root of b squared minus 4ac all over 2a. That's the quadratic formula, right? Well, that's the same thing here. They're saying where would this local maximums be? Well, they'd be at the stationary points. They'd be at the solution to this equation. Okay? Well, the solution to this, according to the quadratic formula, is negative b, whatever's in front of the x. Well, in front of our x is 2b, right? Plus or minus the square root of whatever's in front of the x squared. So in front of our x is 4b squared. Minus 4 times what's in front of the squared term, which in ours is 3a, and c, which is the constant, which for us is c. And then all over 2 times a, which is whatever's in front of the squared term, which for us is 3a. So that's where that came from in 46 part B. So we would just solve this using the quadratic formula. Now you can go ahead and you can factor out some things and you can reduce some things and make it look like theirs does in part B. Okay? But that's where that one, it's a good problem too. I just, I don't want to just gloss over it, but it's, you know, you can kind of put the problems in a couple of categories, and we have some of each on the quiz. I mean, they're the ones you really got to know how to do, and they're the ones that we practice a lot of, these max min kind of problems. And then you get into some of them that kind of are out there a little bit and make us really use those concepts. Now, we'll always throw some of those in, and as we get later in the year, we'll bring in more of those as we hopefully understand the concepts even better. But that's kind of where that problem was coming from. Okay? All right. Let's move on here to what we want to learn. We're going to kind of skip over section 2.5 today, and so we're going to jump ahead to page 132, essentially. Now, what happens in section, I told you this yesterday, but in section 2.5, we're going to talk about something called differential equations. And differential equations are something we will now look at in section 6 and 7 as well. But another part of section 6 and 7 is using what we learned in 2.4. Okay? And that is this max-min business. So what we're going to do is we're going to first do the parts of section 6 and 7 that deal with what we've learned in section 4. Okay? So we're going to kind of pick and choose those things. Now, so far, let's write down our derivative rules that we've learned up to this point. All right? And to be honest, we only have one. And that is the power rule. We're going to add to that today. Okay, that is Leibniz notation for the derivative with respect to x of x to the n power. We bring the power down in front, and we decrease the power by 1. Okay? So the next one we want to talk about is e to the x. Now notice that an exponential is different than the power rule. You know, some people think, oh, you just bring the x down in front. No. No. A power rule is when you have x, the variable, and this is where this Leibniz notation is so important. We're doing the variable is the x. That's different than the constant, the n or the e. Those are constants. When x is in the base, then that's a power rule. When x is in the exponent, that's an exponential. It's a totally different rule. So you do not bring the x down in front. It doesn't work. Now, I think I told you this one day actually about e to the x. Remember us talking about e to the x and what the slopes were? No? Okay.
They're easily.
Aren't they the same? Aren't the slopes the same as the y values? We talked about that. Let's go to the calculator. And I don't know who this is. Jason Shutt, thank you for being the presenter today. Go to the calculator screen, please. And let's set up for him the derivative the long way. Okay? Don't worry about writing this part down. Limit as h approaches 0. What would this look like? Our long form derivative. E to the x plus h minus e to the x all over h. That should be the derivative of e to the x, right? Now, we're learning the shortcuts here, so we don't always have to go through the long way. Now, when we had to do the long way, like on our quiz last week, we then had to do some algebra to this, right? Well, the algebra is not quite as obvious as it sometimes is, so I'm just going to do a couple of things to this first, and then we're going to have him help us on the calculator. I'm going to write e to the x plus h as e to the x times e to the h. Is that correct? Can I do that? Because the rule is when you're multiplying bases the same, you would add the powers, right? Now can somebody tell me what I can do on the top? Take out an e to the x, and I'd be left with e to the h minus 1 all over h, right? Now, one of the properties of limits is when you're multiplying two things, you can multiply their individual limits. So we could split this into the limit as h approaches 0 of e to the x times limit as h approaches 0 of e to the h minus 1 all over h, right? Now, what does e to the x do as h gets close to 0? There's no h in it, so it's unaffected by h getting close to 0, right? So this is just e to the x, all right? But the real question is, what is that limit? So, Jason, actually, I don't want to cheat. Let's go to the graph screen. Let's go to the graph screen, and let's do like we did before the last quiz. Let's type this into F1, except we can't use h, we have to use x, right? So let's go e to the x minus 1 and then right parenthesis that, and then divide it by x. Okay, and hit enter. And now let's go to your menu and let's go to table. Okay, where is that? View, under view, or Control T. Go to our table. Where do we want our table to start? At 0, right? Because we want as x approaches 0. So let's edit our table settings. Let's go 0 and let's put in like 0.00001 there. Okay, and let's arrow up. And what does that limit seem to be? seems to be 1. And sure enough, that's going to come out to be e to the x. Okay? So, the derivative, we've proven it the long way. The derivative of e to the x is e to the x. Okay? Now, let's do something else to the x power. Anything else. We'll call it a to the x power. Okay? Let's do any other base other than e. Okay, like 2 to the x or 3 to the x or whatever. Well, over here on my derivative, this would change to an a, this would change to an a, okay? We'd have all this, right? And this would be a to the x times whatever this is, right? Okay, so let's just make one up now, because I can't put an a in here, it wouldn't know what to do. So let's go into your F1 again. So let's go over to, click over there, hit Control G, is a quick way, arrow up. Okay, and let's change that e to a 2. Let's change it to a 2. Okay? And what does the limit seem to be? Okay, it's some number like 0.693, it looks like. 0.693. That was for 2. It was 0.693. Okay? Now, you're going to learn about this tomorrow on your calculator document that I sent you. But go to the calculator screen now, Jason, just for time, I'm just going to tell you what it is. Type in ln2 and then hit Control Enter. Okay? All right? And so if we tried it with 3, we tried it with 4, whatever. So the rule seems to be what? That the derivative of a to the x would be,
ln x.
no.
ln a. 2 to the x, or a to the x.
It'd be a to the x, see, because the a to the x would still be out here, right? Times, what we got before was 1, right? So we had e to the x times 1. Well, now we're going to have a to the x times ln a, okay? So it's a to the x times ln a. Now remember, ln a is just a number. ln a is just a constant. Now, brings in something else that's special about the letter e. So what we're saying is 2 to the x, 3 to the x, those derivatives are also 2 to the x, 3 to the x, but we have to tack on this extra multiplier, this constant, but not with e to the x. If you think about it, e to the x actually works here. Couldn't we write e to the x times ln e? What's ln 1? Or what's ln e? ln e is 1, right? So actually this rule here encompasses this rule. But since we run into e to the x so much more, we just usually write them as 2 separate rules. Okay? All right, so exponential functions in general are their own derivative. But if you have a base other than e, you have to tack on ln2, ln3, whatever that base is. And again, just remember, that's just a constant right there. All right, because that could get confusing when we go to this next thing. Natural log of x. What's the derivative of natural log of x? Okay, and we won't even work on that one the long way because that one comes out to be, the algebra of that is, all we would do is type it in and put the answer up. The derivative of natural log, let's go back to this. The derivative of natural log of x turns out to be, and it's kind of a strange one, 1 over x. It's the only derivative, logs are the only derivative that don't stay within the same family of functions, right? When you have a power function and you do the derivative, you get another power function. You have an exponential, you do the derivative, you get another exponential. When you do a trig, you'll see in a minute, we get another trig function. With natural log, when you do its derivative, you get this. Now that also brings up something that's kind of interesting. That's x to the negative 1. So what's the antiderivative? So if little f is 1 over x, which is x to the negative 1. What should the antiderivative be? Well, I mean, based on what we've learned right here, what should the antiderivative of 1 over x be? ln x, right? I mean, that's the way derivatives and antiderivatives work. They're backwards. But I'm guessing a lot of you would have said, wait a minute, why wouldn't we use that power rule we learned yesterday, right? Raise the power up 1, x to the 0, divide, there's the problem, right? You can't do an antiderivative with x to the negative 1 with that rule we learned yesterday because you would get dividing by 0. Now, think about what antiderivative means. It means that there's something that when you do the derivative that will get you that. Well, there is nothing you can do to take a derivative and end up with x to the negative 1. You can't, because remember, when you do a derivative, you decrease the power by 1. Well, that means you would have had to start it with x to the 0. Well, x to the 0 is just a constant. It's 1, right? And when you do the derivative of that, you get 0. You don't get another x. So it kind of makes sense. It's kind of the way math always is. When there seems to be a gap, there's always something there that fills it up. And there would be a gap there in 1 over x antiderivative, but it turns out the derivative of natural log is that. Okay? So, that's just one to memorize. And then if you have other base logs, okay, it's going to work very much the same. If we have log of any other base other than e, the derivative is 1 over x times 1 over ln a, the natural log of whatever that base is. So if you're going to do the derivative of log of x base 2, the derivative would be 1 over x times 1 over ln 2. All right? We will have a very large, pretty large list of these rules that we'll just have to memorize. Now, it'll be pretty easy once we, get through. The hardest part is when we start putting them together, multiplying them, dividing them, putting them inside of each other, that kind of thing. But we'll have to know these derivatives by memory. All right, we got 2 more I want to do here. Let's do sine. And I think we talked about this the other day too. I think I showed you a picture of this. One of the classes I did, I know. Anybody remember the derivative of sine x? Cosine of x. All right? Now, again, you don't have to write this down, but I want to write this the long way real quick. So what would it look like if I was going to do it by the definition? Sine of x plus h minus sine of x all over h. Now, not in the algebra, you can't distribute sine through there, but you remember last year doing trig identities, and you did the, one of them was the addition rule. You probably did like sine alpha plus beta or something like that, or a plus b. Okay, if we look, let's turn in our books. I think this is how important those are. I still don't even remember. That's how much I've used them, or we've used them. But if you turn to page 142, the sum formula, right in the middle of page 142, the sum formula for sine expands out to sine x cosine h plus cosine x sine h. So that's all that first one, and then minus sine x all over h. Okay? Now what I can do is I can rearrange the order here. So I can group these two together and separate it with this one. So I can separate this into 2 different functions. I can do cosine x sine h over h plus sine x cosine h minus sine x all over h. All I did, that's separated 2 fractions. They have a common denominator, so I can put them back together if I needed to. All right? On this one, I can factor out a sine x. I get cosine h minus 1 all over h plus I got this one, cosine x. Now remember what I said earlier, how I could split this apart. Okay? So, and remember all of this is the limit as h approaches 0. Okay, so get ready, Jason, on the calculator here again. So, as h approaches 0, the cosine x will be unaffected, so it'll just stay there. Sine x will be unaffected, but what we need to do is we need to do those two limits right there. Okay, so let's put in, Jason put in that first one. Let's go to the graph screen. Okay, and hit Control G and arrow up. Okay, and let's do sine x over x. Whoops, you gotta go out there. You go. Okay, and look at our table. And what's the limit? Limit seems to be 1. So that'd be cosine x times 1 plus, and then do this one. Let's go back to your F1. And let's do cosine x minus 1 on top. Right parenthesis. Nope, hit a right parenthesis there. There you go. Divided by x. And the derivative, or the limit is, what is that limit then? That's 10 to the negative fifth. That's very small numbers. Okay? So that's 0. So sine x times 0. Sure enough, we get cosine x out of all that. Okay? And I like doing this, not that you're going to have to go back and do this, you won't on the next quiz, but again, tie this back to slope between 2 points, because that's all this formula is slope between the 2 points as the 2 points get closer together. All right, and then I think we also did cosine while we were at it. And that was what? Remember? Negative sine x. It looked like sine, but it was flipped over. All right? So that's something we'll have to keep in mind. Now also there's antiderivatives of that, and antiderivatives just work backwards. One of the things you always got to kind of work at is, you know, well, okay, if the derivative of sine is cosine, then that means the antiderivative of cosine is sine. And so it's always easy to mix up. Let's see, the derivative of cosine is negative sine, but the antiderivative of cosine is sine. Which one's negative? The way I always remember that is I just remember this first rule. Derivative of sine is cosine, and then you get the rest from there. Derivative of sine is cosine, so that means derivative of cosine is the one that's negative. And then if I got to go backwards, okay, since derivative of sine is cosine, antiderivative of cosine has to be sine. So the antiderivative of sine is negative cosine. Okay, so those will be things that we'll work on as you go through here. But, and of course we still have to do tangent and secant and all those, but for right now we'll just deal with those derivatives there. All right, I'll help you with one of the homework problems here. I think it's one of the homework problems. Number 37. Let's see. This is page 147. I had mentioned, but before we do this, on 3 through 12, on today's assignment, I mentioned we'd come back to that, and I did. So when we get some work time here, or when we get done with number 37 here, we'll go back to that if somebody wants to, or you can ask me individually. Okay, on 3 through 12. There was some speed limit law in there, okay, and so there were some things with the chart that I want to make sure we understand. Those are important problems. But let's take a look at 37. All right, go ahead and write down that problem. Read the directions. Okay, this is a lot like number 35 that you'll have in your homework today. So the first thing it says, this is a little bit old-fashioned in the sense it says draw a graph of this function. Before we had graphing calculators, we used to do a whole unit on drawing graphs. And you had to do them all by hand and plot points, and you had to go through all this local max, local min, points of inflection. You had to find all that stuff, and then you had to plot them and get a nice curve sketch of what it was. And we had this big, long 10-problem take-home assignment. And we don't do it anymore because with graphic calculators it's kind of pointless. I mean, you just type it in and there's your graph. And so, so it says draw a graph of the function. I don't even worry about that part, to be honest with you. We're not even going to draw a graph. What I do want you to do though is find the local extremes, global extremes, points of inflections. It says with both coordinates. It says use exact values rather than decimal approximations, meaning no calculator. That's what we're thinking about. Okay, so in one problem here, we can just learn a lot about these different things we've been doing here on today's homework, except it's with a trig function. So here it is. It's 1/2 x plus sine x, and we're on the interval 0 to 2 pi. This is a really important problem. You will definitely have one of these on the next quiz. It will be worth 6, 7, maybe 8 points, depending how many of these things I ask you in that one problem. And as we get ready to review, as we get closer to the quiz, you'll hear me say, remember, on page 147, number 37, that's a good one, to review. You're going to have one like number 37. Okay, so put big stars by this one or something. We need to be able to do this. So we're going to find global extreme, local extremes, that's max and mins, points of inflections. Where do we start? Do the derivative, right? So we do f prime, and that would be 1/2 plus cosine of x, right? The new rule we just learned. The derivative of sine is cosine. Okay, then what? Set it equal to 0. And what? Solve it. Now this is what this worksheet you're going to get tomorrow is going to have a bunch of it just solving these problems. Practice solving, because you have to be able to solve. So what do we do in this one to solve? Move the 1/2 over. So we want to find when cosine is equal to negative 1/2. Now, this goes back to the trig review that I did and that worksheet that I gave you, a month ago. 3 weeks, whenever it was. You either have this memorized. What quadrants are we in? The second and third quadrants where cosine's negative. Maybe you remember cast or that stuff. Okay? And where does cosine equal 1/2? What reference angle? Pi thirds. But we're in the second and third quadrant, right? Now maybe you don't have that memorized that it's pi thirds. Then what you would do is you'd come over here and you do SOHCAHTOA. You'd say, okay, -1, cosine is adjacent over hypotenuse. So adjacent over hypotenuse has to be -1 over 2. Second, third quadrant. Well, across from the radical 3, you recognize this as a 30-60 triangle, right? And across from that is the 60 or the pi thirds. So that would be what? Well, this is pi over here. This would be 3 pi thirds. So we're 1 pi third short of that. So we're at 2 pi thirds. Or we are at 4 pi thirds. Okay? Got to be able to solve these trig equations. This is where it will happen, okay? In these kind of problems, in max-min problems, where you do the derivative, it's got a sine or cosine in it, you set it equal to 0, got to solve it. This is when we got to solve it. Those are our stationary points. Okay? Now, in a problem like this where they ask for so much stuff, they just ask for all this stuff. You know, it's almost like those old geometry problems. Remember those geometry problems where you had angles, you had lines going everywhere, and angles all over the place, and triangles, and they wanted you to find this angle over here. Well, but you had to find 100 other angles before you could ever find that one. So you're better off just filling in the whole problem and finding them all, and then write down the ones you needed. Well, that's kind of the way this is. You know, from here I could do my local max, local min by doing what? What would you do next? How did we do the local max, local min? Number line. Number line. Global max and min, we did list of candidates, right? So depending which one you want to do first, if you want to do global max min first, we could do list of candidates. If you want to do local max min, we do a number line, right? Okay? So which you want to do? Number line. Okay, so let's do the local max min. So we'll draw a number line, we'll call it f prime. We'll put our 2 pi thirds and 4 pi thirds on our number line. So now I need some numbers in between here. 0 would be a good one here. What's a good one between 2 pi thirds and 4 pi thirds? Pi would be a good one. Because I'm going to be plugging them back into f prime, which means I got to plug them into a cosine, so I better pick some ones that are easy. What about this one? 2 pi would be a good one here. Okay? All right. And I'm plugging the, now I label this f prime. Really important. Because it's something we're going to do in a minute. All right. So I put a 0, I come back to my f prime. Right here. So I put a 0, what's cosine of 0? Cosine of 0 is 1. You either remember that from the unit circle or draw yourself a quick cosine graph. Right? Cosine of 0 is 1. Cosine of 0 is 1. So 1 plus a half, that's positive. Okay, what about pi? What's cosine of pi? Cosine of pi is right here. Negative 1. Okay? Plus a half, that's negative. 2 pi, cosine of 2 pi is back at 1 again. So we're back at a positive. So that number line now has told me all kinds of stuff. And I'm not going to write it all down now, but I will emphasize to you that on the quiz, there's some very particular ways that you have to write out these answers. If they would know where's this function f increasing, well, we would have it. It's right there. Where is it decreasing? We'd have it. We'd write it out. Local max. Where's the local max? 2 pi over 3, right? F prime changes from positive to negative. Where's the local min? Right here. F prime changes from negative to positive, right? Now they had asked me in the directions of this problem to write both coordinates. So, you know, they were but I'm going to do that when I do my list of candidates here in a minute. So normally with local max, local min, we just care about the x values. So you would write that down. As a matter of fact, whenever you do a local max or min, the answer is, well, what the heck, this is important enough to just do it. You would actually have to write local max, x equals 2 pi thirds, okay? And this is something that AP changed on their testing procedures about 4 years ago. When you do a local max, this number line used to be good enough as justification, not anymore. You have to write out why that's a local max, and it looks like this. F prime goes from positive to negative, so F goes, or changes, you can say goes or changes, goes from increasing to decreasing. You actually have to make that, what they said is they want to make sure people understand the connection between F and F prime. And so in your explanation of why that's a local max, you actually have to reference both. You can't just say, well, since F prime changes positive to negative. You have to say, therefore, F changes from increasing to decreasing. That's what makes it a local max. And you have to do the same thing for local min. Okay? All right. if we were going to do a list of candidates now, we would do our list of candidates. We would use 0, 2 pi, 2 pi thirds, and 4 pi thirds, and we would plug those back into the original. And we would get those values for our global max and min. Okay? All right. But we're not completely done yet, because what's another thing they ask for in those directions? Inflection points. Where do the inflection points happen? Remember we did that earlier today? You look at the chart, it's where the second derivative is 0. Those are your possible inflection points, but you do a number line to check and see if it changes sign. So what we need to do to finish this up is we need a second derivative. Okay, this is in one problem here, we really get a lot of the things you have to be able to do. It won't always be in one problem. Some of this will be spread over multiple problems. But what is our second derivative? Negative sine of x. And we're going to set that equal to 0. Remember, we always said second derivative is mostly about concavity. That's where you go for points of inflection. So we have to solve this. Well, when does negative sine x equal 0? Well, you can divide by negative if you want, if that bothers you having that in there. Good thing to do is graph negative sine x. That's an easy thing to do. You know, negative sine x is 0, all the same place as sine is 0, right? Which would be at 0, pi, and 2 pi. Now, typically as a rule, we do not include inflection points and local max mins at the endpoints, just because we don't have information on each side. I'm not even sure in the back if they did include that or not. I'm going to say let's don't include points of inflection as our endpoints. All right. So I'm going to label this F double prime. I'm going to put pi on there. Because local max, local min, and inflection points, we always want to see on both sides of it to tell if it's changing, concavity, or if it's going increasing, decreasing. So at the ends, we usually won't include those. Might be wrong on points of inflection, but for right now, let's don't worry about that. So we'll put a pi in there, and we're going to plug into our F double prime. So now, of course, then the thing everybody wants to do is what's a number less than pi? They put 0. Well, what's wrong with that? When I put that in, I'm just going to get 0, right? I'm not going to get a positive or negative. So we don't want to do that. We're going to have to do something like pi halves. Okay? And we're going to have to do something over here like 3 pi halves. So let's put it in. What's sine of pi halves? Positive 1, but then the negative will make it negative. 3 pi halves, sine is negative 1. The negative turns it to a positive. But what does this number line tell us? So therefore, F prime has a local max min, but more importantly, F has a change in concavity. What we just found here is that F prime has a local min, but actually we don't care about that, other than local mins of F prime are where F has inflection points. But basically we saw a change in concavity. So what we would say, and again, we might label these possible inflection points right here. These are possible inflection points where the second derivative is 0. The number line tells us, hey, it is an inflection point. We'd say x equals pi is an inflection point, and the reason, and it would be much like the reason there. F double prime goes positive to negative, so F goes, oh wait, that wasn't positive, negative, my fault, negative to positive. So F goes concave down to concave up. That's why we have an inflection point, because there's a change in concavity. All right. So these take a little time. You got to put some time in on these. Okay. And don't wait till next Tuesday and say, oh my gosh, I got to, come in and see me. Come in and see me if you want some help. On section 2.5 homework. Actually, no, not 2.5. We're going to do it over a couple of different sections here. We're going to go Let's go out of 2.6. Let's do 6, 8, 16 through 30 even. Now what those are derivatives, and it looks like a lot on 16 through 30, but they're just using these derivative rules. Okay, like remember we talked about the shifting and stuff like that. I'm going to show you an example here in a second. And then doing a second derivative, and then doing an antiderivative. Okay, so that's what that whole section there's about. And then number 35. Okay, and on 2.7, we're going to do 10 through 13. And I'm not going to have you do one that's quite one of these real long ones like this just yet, but on 2 through 7, which is page, what page was that, 149, 150? No, 140. 147. Starts at 147. Let's do 10 through 13. Okay, so basically that's a problem a little bit like number 37, but it's broken up into 4 parts. One is find a local max, one's a local min. Okay, so you kind of go through that a little bit like that. And then the rest of it we'll just do 18 through 34 even. And then that is, again, just like that 16 through 30 even. That's just a section where some sines and some cosines and you're doing the derivative. Practice doing the derivative, do a second derivative, do an antiderivative. Okay? All right. Tomorrow you'll have some stuff in class to work on, and there will be a book assignment. There'll probably be a small book assignment to go along with that, so you'll have this in-class stuff. Whatever you don't get done in class tomorrow will be part of your assignment for Thursday, but a lot of this won't get checked till Thursday, obviously, since I won't be here tomorrow. I hate to even say that because now all of a sudden you got registered and what you heard was, oh, this isn't due till Thursday. Great. Got the night off. Well, no, there will be a few additional things too. So, and you may have some that you don't get done in class tomorrow. So try to get this done for tomorrow. If there's some things you still didn't get answered for questions, I won't be here in the morning, so stop and see me after school tonight would be great. Lunchtime.
Or you could text me.
I should have had you come in early this morning.
I don't have tennis tonight.
Okay. Well, again, it's kind of like what I did today. We're going to kind of mix. So tomorrow, you'll be here tomorrow. But I'm actually, you get that stuff. So on Thursday.
And today I don't have tennis,
I don't
so I'm
know
not going
for
home right away. I can chill for a while.
I mean, I'll have the video.
I generally don't start my homework till like
Yeah, I don't know that.